Right, this is the video to explain how to do question 2 of those 2 questions that I sent you yesterday. If you haven't gone over question 1, please do. You'll see lots of colourful sketchy diagrams all over it. Brilliant. And I'm going to do the same with this one. You must use the circuit diagram to assist you. Don't try and keep the information in your head, put the information on the page. Right, let's get cracking on this one then. So we've got no context in this question really, it's just a straight up, this is the circuit, analyse. The student connects 4 lamps A, B, C, D in the circuit. Battery has an EMF of 9 and a negligible internal resistance. Now we always like to see negligible internal resistance. It means that we can just take that as the EMF, 9 volts there. And if we know 9 volts across there, we'll know 9 volts across there, 9 volts across there. Up to yet, that is all we know. Right. The table shows the operating conditions for the lamps when they're at normal brightness. Right, normal brightness would imply that this is the operating conditions, and in the operating conditions you would have a power rating, P, you would have a voltage at which that power rating would be set, you'd also have a current at which that would be set as well. Of course we know there's a formula that links all those three, P equals IV, and its variations, P equals I squared R and P equals V squared over R as well. Alright? We did that at length a couple of weeks ago. Now, right, so A and C, B and D. Right. The operating voltage of A and C, so A and C are the same, is 6 and the power is 6 watts. And the operating voltage of B and D, the ones on the right hand side, are 3.5 volts. And the question goes thusly: the student observes that 2 of the lamps are at their normal brightness. Assume that any changes in resistance of the lamps are negligible, so they stay at, there's a bit of a clue there really. Determine which 2 lamps are at the normal brightness. Use calculations to support. Right, now, if these lamps, A and C, or B and D, in fact let's add a bit of colour to show that these 2 are the same, and these 2 are the same, right? So we've got A and C and B and D. Which ones would be at their normal brightness? Well, they would be the ones at their operating conditions, right? So let's use this information. It gives us a table. Why would it give us a table? Because we're going to use the information in it. I want to know the resistance of these lamps. Using that formula there, R equals V squared over P. So to get R for A and C, I'm going to do V squared over P, so it would be 6 squared over 6, 36 over 6, 6 ohms. Right? B and D is a bit different. B and D we've got 3.5 squared over 4.1. I'm going to chuck that in the calculator because I can't do that mental arithmetic. If you can, then you're better than I am. Well, 2.98, and I think for ease of stuff we're going to call that 3 ohms, right? Because it's practically 3 ohms, isn't it? Ridiculously close to 3 ohms. Right, so I'm going to put that on the diagram. I'm going to say that A and C are 6 ohms, 6 ohms and 6 ohms, and I'm going to say that our friends here are 3 ohms, not blue, no, and 3 ohms, right? That should be in green, but never mind. Right, so what is the operating current of, what's the current going through it? So now, to be fair, it's quite lucky for us because 9 volts goes in there, which means we've got 9 volts across here, 9 volts across here. What makes the numbers easy and nice for us is we've got 9 ohms there. So the current up here is 9 over 9, which is 1 amp. And down here, 9 over 9, which is 1 amp. The 1 amp goes through both. Now we need to know, right, okay, which one is going through the same, which one is wants 1 amp, right? Using the data from down here, P equals IV, I equals, for A and C we've got P over V, so we've got 6 over 6, 1 amp. Sorry, kids shouting all in the house. Right, 1 amp, so that should suggest that A and C want 1 amp. We've got 1 amp, so A and C should be at the normal brightness. But let's just make sure. Right, so for B and D, PIV, so I equals P over V. P is 4.1 over 3.5. And that answer is 1.17, 14285, about 1.17 amps. Hence, this A and C would need 1 amp, B and D would need 1.17. Now we've just kind of established that it's 1 amp going through each branch of that parallel circuit. So which ones are working at their normal brightness? A and C. And all this calculation would of course go in this area here. I was just trying to keep it close to the circuit. Alright. Okay, moving on. The student connects another lamp E. I love this question. The students have some fun with this one, let me tell you. Right, the student connects another lamp E in the circuit as shown. Right, E is identical to A and C. So just because we know this stuff, these are 6 ohms each, and these are 3 ohms each. Okay, explain what the student would observe when regarding the brightness of the lamps when E is put in. Now, I hope you've had a go at it. It's a bit of a trick question. Why is it a trick question? In fact, E will not illuminate or light up. Right? Why will it not light up? Okay. Let's think about what potential difference means. There's a theme running between these two questions, which is why I've given you both, right? Comes in here, 9 volts given, 9 joules per coulomb. Comes to the parallel network. We've got a ratio of 6 and 3, which makes it easy for us because we lose 6 volts over there and we lose 3 volts there. 6 volts and 3 volts. Now also, coming down here, we lose 6 volts, we lose 3 volts. And they come back together and they get 9 volts, 9 joules per coulomb, 6 joules per coulomb, 6 joules per coulomb, 3 joules per coulomb, 3 joules per coulomb. Right? Now E is connected across here and here. So at this point here, we've got 9 volts, we've got 9 volts. We lose 6 volts. What do we have at this point? Of course, as we go away, we've got 0 volts. But what do we have at this point and this point? Well, at this point here, the electrical energy in there is 3 joules per coulomb, right? And also here, we've got 3 joules per coulomb. So, what's the potential difference between this point here and this point here? Well, the potential difference is 0 volts. And if there's no PD, then we have no current. And if we have no current, then the bulb won't light because it's not being given any electrical energy. There is no current flowing through E because there is no PD across E. And for current to flow, you need PD. Now, I mean, it's a trick question. Your mind considers, that if E is there and it's a bulb, you just put another bulb in the system, it'll light up and they'll all go dimmer, which is where a lot of students think. But this question is really testing your understanding of potential difference. It's a nasty question, really. It's a trick question, but it's one that separates out, the A graders from the DE grades. They have to do that in a paper. All right. Okay, can you do you understand the idea of that? And all the other bulbs will stay exactly as they are. If you put a voltmeter where E is, it would read 0 volts because the potential energy here and here is exactly the same. Naughty question. Lovely question for them, if you look at it from one way. Right, final question on this one. Lamp B in figure 2 fails so that it no longer conducts. This change does not affect the resistance of the other lamps. Deduce the effect on the current in the battery. Right. What current did we initially have? So if we go to this circuit here, we knew we had 1 amp up here and we had 1 amp here, which means that the current in the battery is 2 amps. Right, so we're going to put a pin in that. We knew we had 2 amps before. If B fails, right, so what we're saying is with this picture here, B is going to fail. And a lamp, when it fails, basically breaks the current. So what happens is that then disappears. And the circuit will continue, but with B disappeared. Now we could potentially use this, but my advice on this question in particular would be to redraw it out. And I have given you a bit of space to do that. So let's look at what we've now got. The negligible internal resistance remains the same, 9 volts. We come up to here now, and we still have a parallel network, but it's changed slightly now. Now we have A and E in series with each other, which is in parallel with C, and then it goes down through D in series with that. That's what effectively now the circuit is turned out to be like. Can you see why? I'll try and put the 2 circuits next to each other. I can't really, but A and E are in series with each other, which is in parallel to C, which then goes through D and out. Right, so the electricity comes in here, or the energy comes in here, it then gets split that way, comes back, and they both go through D and then come out, and that's effectively what circuit we've got now. Okay, so let's work out, well, A, C and E are all 6 ohms. 6 ohms, and D now is the only one there with 3 ohms. So what we need to do is we now need to calculate the resistance across here. Well, this is 12 ohms and 6, so RT, 1 over RT equals 1 over 12 plus 1 over 6. 1 over 12 plus 1 over 6 equals a quarter. But we need to inverse that answer. One over the answer gives us 4 ohms. So this now becomes an effective network of 4 ohms, and we add that to that one, because now we've got a 4 ohm network and 3 ohms together, so that effectively the total resistance in the whole series is 7 ohms. Now, what's the current going through the cell? Well, the whole resistance out here is 7 ohms. So we have got I equals V over R equals 9 over 7. One 1.285714 amps. Let's round it to 1.3 amps to sig fig. So did the current go up or did the current go down? I before equals 2 amps. I after equals 1.3. It's because it's gone in series with one bulb only there. So therefore the current has decreased. So current has decreased, right? Now, you know, again, simple when you've been given the answers, simple when you've been shown how to do it. It's much more difficult when you're in an exam condition and that is thrown there. But hopefully you understand why I've chose to go through those ones. They are quite challenging, but they're not impossible once you know the way to do them. Alright, so hopefully that's been worthwhile. Please let me know how you got on. Speak to you soon. Have a lovely week. Bye bye.